Hello everyone, this is Mr. Appel, and we're going to continue with circles today. So last time we learned about central angles, and we learned that the central angle was always equal to the arc that it intercepted. So in this example you see central angle ADC, and I'm just going to show that angle measure. In this case it's 50 degrees. I could make it be whatever I want, but let's just make it a nice even 50. Okay. And of course we know that the arc that it intercepts, in this case arc AC, is equal to that central angle. Okay. Now I'm interested in this inscribed angle and the arc that it intercepts. So angle ABC, notice I've constructed to intercept that same arc. But do you think that angle ABC, this angle here, is equal to this angle? Well, it sure doesn't look the same, right? It sure doesn't look the same. And in fact, it's not. It is conveniently, drum roll please, it's half. It's half the measure of that central angle. So the inscribed angle is always equal to half the intercepted arc. Fairly easy to remember. I have a really catchy song that's going to help you remember it, or it's going to make you groan. Either way, hopefully it helps you remember. The vertex is on the circle, the angle is half the arc. And that's going to help you with something else a little bit later too. But anytime the vertex is on the circle, then that angle is equal to half the intercepted arc, as opposed to the central angle where the vertex is the center. So it's all about the vertex of the angle. That's what you should be paying attention to. Now what you should notice, it's kind of interesting here, is that wherever I put point B, it's still intercepting the same arc. It's intercepting arc AC. And so if the vertex is on the circle, it's half that arc. So no matter what I do, notice that angle measure here, ABC, stays 25 degrees, no matter where on the circle it goes, which is kind of cool. Maybe not so intuitive, but kind of neat. It stays the same, and it doesn't matter what angle I pick. You could even pick an obtuse angle. It's still going to be half. And it's the same no matter where that vertex goes. Kind of cool. Okay, so what we've got here then is, again, inscribed angle is half the intercepted arc. So here's an example. Here I've got this arc that measures 44 degrees. If I want to find the measure of angle A and angle B, so again, angle A, the vertex is on the circle, so it's half the intercepted arc. So if the intercepted arc is 44, then this is 22 degrees. And angle B here, angle CBD, is intercepting that same arc, so it's also going to be 22 degrees. Okay, moving on. Now, what about this situation? What about this? So now instead of two, if I go back a step, that inscribed angle has two chords, right? It's made up of two chords, or two secants, really. Here I've got a tangent and a chord, or a tangent and a secant, right? A tangent and a secant. And so I'm interested in this angle and how it relates to the intercepted arc. Well, the intercepted arc, it's a little tricky here, but if you just sort of imagine what part of that circle would get cut off by that angle, or what part of that circle is inside that angle, well, it's this arc. It's arc AB. That's the intercepted arc. And it's still half the angle. The angle, I'm sorry, is still half the arc. So if that arc right there was 140 degrees, then that angle would be half. It would be 70 degrees. So again, the vertex is on the circle, the angle is half the arc. We're never going to forget that. Okay, so moving on. Now let's take a look. Remember we mentioned earlier that cyclic quadrilateral, or inscribed quadrilateral. So I'm interested in if there's anything interesting about a cyclic quadrilateral. Of course there is. We're going to look at two opposite angles in the cyclic quadrilateral. So let's just pick angle X and angle Z. Well, it's a cyclic quadrilateral, which means the vertices are all on the circle. So let's look at the arc that's intercepted first by angle X. Well, that arc is going to be this arc, arc WZY. Okay, and now let's look at the arc intercepted by the opposite angle, angle Z. I'm going to change colors here, so if that's angle Z. The intercepted arc is going to be this arc. Now I have no idea right now what the measures of those angles of that arc is, but what I do notice is that those two arcs together, this blue one and this green one, make a circle. Right? They make a circle because they meet at the same point here. Right? They kind of stick on W, I'm not saying this very well, but W and Y. So they cut out, if the two combine, they cut out one complete circle. The green arc and the blue arc together are going to make a circle. Well, if the green arc and the blue arc together make a circle, what does that measure? That's 360 degrees. But what do we know about the inscribed angles? While the vertex is on the circle, the angle is half the arc. So X and Z combined intercept 360 degrees, which means they must equal half that. They must equal 180 degrees. So opposite angles in a cyclic quadrilateral add up to 180. They are supplementary. So in this example, X and Z are supplementary, and W and Y are supplementary. Kind of cool. Okay. Let's look at some examples using what we just learned about. So first here in number 4, if this angle is 38 degrees, the intercepted arc must be double that, right? Because the angle is half the arc. So if that's 38, then this is 76. But then angle X is also intercepting that same arc. And again, the vertex is on the circle, the angle is half the arc, so that's going to be 38. And angle Y is also intercepting that same arc, so that is also going to be 38 degrees. All three all three inscribed angles intercepting the same arc, so they're going to be equal. Okay. Now, let's take a look at number 5. So now they're telling us here that O is the center of this circle, which makes this here a diameter. Okay, that's a diameter. So what that means is this whole thing is half a circle, a semicircle, which is going to be 180 degrees. Well, if that's 180 degrees, if this is 50, then this part must be the rest. That must be 130 degrees. So if that's 130 degrees, angle Y, notice angle Y has its vertex on the circle. You know it's coming. The vertex is on the circle. The angle is half the arc. It's half that arc, so that Y is going to be 65 degrees. Okay. And angle X here, I could have done angle X first. Angle X is here. This is getting messy, so I'm just going to do some erasing because that's a big mess. Angle X is angle X is an inscribed angle that intercepts that 50 degree arc, so it's half, so angle X is 25 degrees. Number 6, this is a cyclic quadrilateral. I know that because it's a 4-sided figure with all the vertices on the circle. So opposite angles are supplementary, so 110 plus X has to be 180, so that's 70. And 85 plus Y has to be 180, so that's 95. Very little work there when you know it's a cyclic quadrilateral and the opposite angles are supplementary. Okay. Now, a couple more new things here. Now we've got some weirdo situations. So now that vertex, it's not in the center of the circle, and it's also not on the circle, but it's in the circle somewhere. So what happens here, this angle, angle 1, is actually, if you kind of go in both directions, it's intercepting two different arcs. This arc is intercepted by this angle 1, but this angle 1, remember those are vertical angles, so they're equal, is intercepting this arc. So which arc is it? Well, it splits the difference. It just average them. So it's still half. It's still half. It's just half the sum. It's just the average of those two arcs. And that's called the chord theorem if you're keeping track at home. But that angle there, which doesn't really have a special name, it's just formed by those two chords intersecting, is equal to the average of the two intercepted arcs. Kind of a weird situation there, but we'll get into that more later. A couple more weird situations now. We've had a vertex that is the center. We've had a vertex inside the circle. We've had a vertex on the circle. Now we're going to have a vertex outside the circle. Outside the circle. And there's 3 different cases. I'm going to actually look at this third case here first because it gets the easiest to visualize. So if my vertex is out here and I have 2 secants, so 2 lines that cross through the circle twice, so there's one and there's one. Notice now there's not just one intercepted arc, but 2. There's this bigger one and there's this smaller one. Okay, so if the vertex is outside the circle, the angle, this angle, is half the difference. So it's still half, so all you have to remember is that it's half. So if the vertex isn't in the center, it's half. Half of what? Well, when the vertex is outside, it's half the difference between the 2 arcs. And if you notice, that can happen in all 3 of these situations. So here we have 2 tangents. So again, the vertex is outside the circle. This one's kind of weird to see, but if it cuts the circle there and cuts it there, it does create 2 different arcs. This smaller one, the first one, and this bigger one, the second one. Okay. So again, it's half the difference between them, the big one minus the small one. And then when you have 1 tangent and 1 secant, it still intercepts 2 arcs. You've got this little one, and then you've got this big one. And again, it's half the difference in all of those cases. So let's look at a couple examples of how this would apply. So this first example is, you see we've got the vertex, just focus on the vertex. The vertex is inside the circle, but not the center. So that angle is going to be half the sum. So add them up and divide by 2. 40 plus 30 divided by 2. 40 plus 30 is 70 divided by 2. So that angle is going to be 35 degrees. Okay. Now here's another example. Okay. Here, notice the vertex is outside the circle. So it's half the difference between the 2 intercepted arcs. There's the bigger one. There's the smaller one. So it's half the difference, so 120 minus 40 divided by 2, which is 80 divided by 2, which is 40 degrees. Okay. And that's just a coincidence that it happens to be the same as that particular arc. Okay. Now here's kind of a funky situation. Let me make a little room here. Get rid of that since we're done with it. Okay. So now here I've got again a vertex that's outside the circle, so it's half the 2 arcs. There's the big arc and there's the little arc. But what's the little arc? Well, it doesn't tell me, but we can actually figure it out because in this case those 2 arcs combined have to add up to 360 because it's a whole circle. So if this is 260, subtract that from 360 and we get 100 for the other arc. And now you can do half the difference. 260 minus 100 divided by 2. That's 160 divided by 2. And so that angle is 80 degrees. And that's it for today. Thanks.